So today we'll look at implicit differentiation, and we'll see what is the difference between an implicit function and explicit. And then we'll use implicit differentiation to find the derivative of a function and finding derivatives of function using logarithmic differentiations. So you have been accustomed to seeing something written in explicit form, okay? And what do we mean by that? In the explicit form, okay, when you see something in explicit, what really we mean is that it's always in a form where it's y equals. So for example, y equals to 2x plus 3 is an explicit form, okay? So most of these equations, when you see it in the term of y equals, that's the explicit form. Okay? On the other hand, if I have, let's say, x, y is equal to, let's say, 1, this is an implicit form. Okay? So the explicit just means that we can isolate the y, and then y is by itself. So notice that if a function is implicit form, sometimes we can convert implicit to explicit, because if you take the implicit form x, y equals 1, which is implicit, okay, and if you divide both sides by x, you'll get 1 over x. This is now explicit form. Okay, so a very common implicit equation that you've seen, very common, of an implicit form is x squared plus y squared equals 1, right? So this is not a function, but it's an implicit form, and because x and y is not, or the y is not by itself, so it's not an implicit form. So they're very common out there. Okay, so as a note, explicit, okay, explicit form is when the function has the variable y isolated or written by itself. Yeah. So there are many different examples of this. Linear, for example, f of x equals x squared plus 2x plus 3. Okay. G of x equals to the square root of x plus 1. H of x equals 1 over x plus 2. These are all explicit. Okay. Now, when you were given a function, okay, so let's just take a little side note here. Because this is really going to get, and the side note is to lead into the derivatives of implicit functions. So when you were given a function, if you are given a function y is equal to 2x cubed plus 4x, and you were asked to find the derivative, okay? And you're asked to find the derivative of this. What we usually do, we said y prime or dy dx, okay? So, but what's happening really, you say dy dx is equal to the derivative of 2x cubed, okay? The derivative of this would be equal to 6x squared, okay? And then the derivative of plus 4x will be 4. Okay, each one of them you take the derivative of. Now, realistically, what's happening here is that we have this. Y is equal to 2x cubed plus 4x. Well, you see this as dy dx, but there's something happening in the background that you don't really understand. Why do we write this dy dx? Well, the derivative of y, okay, take the derivative of y, which is called dy, okay? And because we're taking it with respect to x, okay, that's where we get dy dx. So the derivative of y is dy dx with respect to x. And then the derivative of this here, because it's respect to x, we don't need to write dx. So this becomes 6x squared. And the derivative of this here, since the variable is x, we don't need to write dx, it just becomes plus 4. So you have to understand when you take the derivative of y, this here, okay, is the derivative of y. That's what it is. So why am I going into detail with this? The reason is because if you have a function, okay, that's written implicitly, you will see why I'm doing this, okay? So let's look at an example here. For example, if I ask you to differentiate x cubed, okay? So d with respect to x, okay? With respect to x. And it's very important. So d of x cubed with respect to x, d dx. Okay, now these variables should look alike, so I'll make sure that they are alike. Let's write them the way, because if they're not alike, then you have to write it. So what is this equal to? Well, this here we know is 3x squared. So one thing to note is that this variable and this variable here, they must be the same before we can end up with this. If they're not the same, then we have to use implicit derivative, okay? We'll have to use implicit derivative. So if we look at another example now, where we have differentiate x cubed, or let's make it y cubed now, okay, with respect to x. And when we say respect to x, that's what we usually do. We're common to take differentiation respect to x. So what is d now? With respect to x means I must have it dx. And I'm differentiating the function y cubed. Now we have to use the differentiation rule. So remember, the rule is that the power comes out to the front, so that becomes 3y, and we subtract 1 from the power, which becomes a 2. But because we're taking with respect to x, and this is not a function of x, okay, not a function of x, we have to say dy dx. So how do we know we have to do this? If you notice here, okay, these variables here are not the same, okay? So when they're not the same, we must use the chain rule, okay? We must use our chain rule. And remember what the chain rule is, right? So if we recall what the chain rule, okay? So as I said, if you recall what the chain rule is, right? So recall the chain rule. Which really tells that d dx, meaning the derivative of the function f, unless it's a function f of some variable u, this will be f prime of u times u prime, okay? Which really means is the simple way, or simplified, okay? It's d dx of u to the n is really n u n minus 1 times u prime, okay? And that's really what we did in the example, okay? If we look back at the example, we have, right, y cubed, okay? We're looking at this example here, okay? So n here, n is equal to 3, and u is equal to y. So the formula says n times u n minus 1 times u prime. So n is 3 times u here is y cubed. So it would be y cubed minus 1, and then the derivative of u. Well, the derivative of u is just dy dx, because I'm taking it with respect to x, dy dx. Okay. If it was du, then it would have been du dx. Okay. So that's really how we're getting the whole answer, dy dx. So let's look at another example. Find the derivative of x plus 3y with respect to x. Now, if they say, just another way of saying this is to say find dy dx. Okay, I'm just pointing out its respect to x right now. So d dx of x plus 3y. So we know that the derivative of the variable, this is the same as d dx of x plus d dx of 3y. So notice here the variable does not match, okay? Does not match. Okay. So taking the derivative now, since these variable match, okay, then the derivative of x would be 1. Okay. The derivative of x is 1. So this becomes 1. Since these variable here does not match, right? Here it's an x and here it's a y, then we have to use the chain rule. Okay. So we'll use a chain rule just as we did above here. So we'll take the derivative of it, the function. So the derivative of 3y is just 3. But because now we have to use the chain rule, this becomes dy dx. Yeah. So anytime the variable is not or does not match, you have to do implicit derivatives. If we look at this example, find the derivative of or better yet, let's start writing it. Find dy dx of xy squared. So notice that this here is in implicit form. Implicit form. So d dx of the function xy squared. That's what they're asking. Well, here we have to use the product rule. Okay. So what is the product rule tells us? Since this is a product, we're going to use a product rule. So the product rule says to first differentiate x, then we add the differentiation of the y. So what is d dx of x, and we keep the second function, okay? So we're really doing this here. And then plus, we leave the x, and then d dx of y squared. Okay. So the derivative, since this is the same, these variables are the same, this becomes 1, the y squared stays, plus the x stays now, and the derivative of this here, you have to use the chain rule. Okay. So this becomes x times 2y dy dx. Okay. If we simplify this, this will be y squared plus 2xy dy dx. Okay. Or if you want to write it the other way, you can also write 2xy dy dx plus y squared. Either way, it's correct. So here we have the guidelines, usually 3 steps, 4 steps, depends on the way the function is written, okay, that will follow. So if I ask you to find dy dx or f prime of y cubed plus y squared minus 5y minus x squared equals -4. Well, we'll differentiate both sides with respect to x. So let's differentiate both sides, right? First rule, step 1, differentiate both sides, okay, with respect to x. So what we're doing, this here is step 1, okay? What does that really mean? It means what is d dx of y cubed plus y squared minus 5y minus x squared. We're going to differentiate that. And we're going to also differentiate d dx of the minus 4. So we're differentiating both sides, okay? Now, since these are all sum, we're going to differentiate each one of them. So if we separate it, okay, this is just d dx of y cubed plus d dx of y squared minus d dx of 5y minus d dx of x squared, and that is equal to d dx of negative 4. Okay, so here, once the variable doesn't match, okay, once the variable doesn't match, that's when we will start to differentiate. And so we didn't quite move to step 2 yet, okay? So let's differentiate. Different. Notice the variables here are different, okay? So we have to use the chain rule. So if we differentiate that, we have 3y squared. Because the variables are different, we end up with dy dx. Notice here the variables are also different. So we have plus, we're going to differentiate 2y, but we have to get dy dx. Notice here the variables are also different. So we have minus the derivative of 5. A y would be 5, but then because we have a y different variable, we have dy dx. Minus, these the variables are the same, so we don't need that dy dx, it just becomes 2x. And equal to the derivative of a constant is 0. Okay. Now we move to step 2. Okay. Now we move to step 2. So step 2, okay, is where we go over here, and it says collect all terms involving dy dx. So what we're going to do is leave all of the dy dx by itself. So we're going to leave this term by itself, this term by itself, and that term by itself. So we end up with 3y squared dy dx plus 2y dy dx minus 5 dy dx equal to, and we take this to the other side, so that becomes 2x. Okay. Now we move to step 3. Okay. Step 3 says that we factor out, okay? So we're looking at step 3 now, which is step 3 over here, says factor out dy dx, okay? So if we factor out the dy dx, we have dy dx, and if we factor that out, we're going to have 3y squared plus 2y minus 5, and that is equal to 2x. And then finally, step 4 says solve, right? Step 4 says solve for dy dx, okay? So solve, remember solve means just to isolate. So step 4, we isolate dy dx. So dy dx, dy dx, since this here is a product, okay? taking it to the other side, will divide. So that is divided by the whole parenthesis 3y squared plus 2y minus 5. And that's our final answer. We don't need to write it with the parentheses. So dy dx is equal to 2x over 3y squared plus 2y minus 5. And that's totally derivative of an implicit function, because this function here given, okay, if you notice that this function here was implicit, right? Y was not by itself, okay? Implicit function. So there's a series of steps to follow, and once that series of steps is followed, then we just solve and isolate. So let's look at another example, okay? So we're finding dy dx, okay? We're still finding dy dx, but now we're using implicit differentiation. The reason I specify implicit differentiation is that sometimes you can solve the function for y and use it explicitly. In this case, I don't want you to do that if you could, okay? So remember step one, right? Step one says to differentiate both sides. So d dx of x cubed y cubed minus y and d dx of x. And then we could separate this, okay? We could separate this. This is the same as d dx of x cubed y cubed minus d dx of y and d dx of x. Now notice here we have a product, okay? So if this is a product, we have to use the product rule, okay? So you may want to go back and look at your product rule, okay? So we're going to differentiate x cubed and we keep the y cubed, and then plus we now keep the x and differentiate the y cubed minus, okay, that's the product rule, okay? This is our product. And then d dx of y equals to d dx of x. So the product rule is what we apply here because there's a product here. Now, since the variable here match, okay, this just becomes 3x squared, and then we bring down the y cube. Plus, over here we keep the x cube, and we differentiate this now with respect, since the variable here does not match, okay, does not match. So this becomes times 3y squared dy dx. The variable here does not match, so minus the differentiation is y is 1, but we need dy dx. And since the variable here match, this just becomes 1. Okay. So that's the differentiation. Now we collect all the dy dx. Notice we only have two terms with dy dx, this one here and this one here. So this will go to the other side. So x cubed 3y squared dy dx minus dy dx, we don't need to write the 1, is equal to 1. And if you take this to the other side, then we end up with minus 3x squared y cubed. Now we factor out dy dx. So we have dy dx in brackets will leave me with x cubed times 3y squared minus 1. is equal to 1 minus 3x squared y cubed. And if we now isolate dy dx or solve, so dy dx is equal to 1 minus 3x squared y cubed divided by x cubed 3y squared minus 1. Or another way of writing it, you could say 1 minus 3x squared y cubed divided by 3x cubed y squared minus 1. Because these are all products, so the order doesn't matter. And this is your dy dx. So here's another example where you're asked to find the slope of a tangent line to the graph at some given point. So you're given a point, so you have an x and a y, right? Now we know find the slope means we have to take the derivative of this. So if you look at this, you could distribute y. This is the same as x squared y plus 4y is equal to 8. And I think it will be easier to see that the derivative here rather than taking the derivative of here as the product using the product rule. It doesn't matter. You'll get the same answer. So if we take the derivative of this, since it's implicit, we'll take the derivative of both sides with respect to x. So x squared y plus 4y, and that's equal to d dx of 8. Now here we have a product. So at some point we'll have to use the product rule, but we could separate this since it's the sum x squared y plus d dx of 4y is equal to d dx of 8. Now this here is a product, okay? So we have to use the product rule. So d dx of x squared, and then that's the first part, plus now we keep the first part and we take the derivative of y plus d dx of 4y equals d dx of 8. So the variables here are the same. So this becomes 2x. And don't forget, we keep our y. Okay? Then x squared stays. The variables here are not the same. So we end up with y, the derivative of y is just 1 times dy dx. Okay? The variables here are not the same. Okay? So this becomes plus the derivative of 4y is 4, but dy dx. And the derivative of any constant is always 0. Okay, so the variables here are not the same. Now we isolate dy dx. So this term will go to the other side. So x squared dy dx plus 4 dy dx is equal to minus 2xy. There's no need to write plus 0, so that we leave it out. Factor out dy dx, so dy dx, and now we have x squared plus 4, and that is equal to minus 2xy. So finally we have dy dx is equal to minus 2xy over x squared plus 4. So this is the slope at any x and y. Now you had a specific, you wanted to find the slope at the point, okay? Your point given is 2, 1, right? This is your point here, 2, 1. So we want to find the slope of the point 2 comma 1. Keep in mind that this is x and this is y. So your slope dy dx would now be equal to minus 2, x is 2, y is 1. And we plug in again, x is 2 and y is 1. There's no 1 in the denominator. So this is a slope at 2 comma 1. So dy dx is equal to minus 4 over 4 plus 4, which is equal to minus 4 over 8, which is equal to minus 1/2. So the slope is minus 1/2 at 2 comma 1. Okay, so that's the slope of the tangent line. Now if you were asked to find the tangent line, okay, you could take it one step further. If you were asked to find the tangent line, you have the slope and you have a point. You can use the point slope formula and find the slope of the tangent line at that given point. So in our next example, we do want to talk about finding derivative of function using logarithmic differentiation. Now, sometimes we make things easy, all depends on the method we use, right? So if you look at this example that I'm about to show here, example, find the derivative of y equals x minus 2 squared divided by the square root of x squared plus 1. And you're given that x cannot be equal to 2 in this case. Okay. Now, you could go ahead and use the quotient rule here, right? Because it is a fraction. Anytime you have a fraction, you could use the quotient rule. Okay. So if you look back in the prior video or notes, you will see we talked about the quotient rule. Alternatively, you could use logarithmic differentiation. And what do I mean by that, right? So you have the option to options, okay? You could use the quotient rule, or you could use logarithm differentiation, okay? Okay. Now, if we choose this method, because I want to choose this method to show you, sometimes it makes life a little bit easier because we know how to use quotient. And I would advise you to use the quotient rule, okay? Use the quotient rule for practice purposes. So for this purposes, I'm going to show you the logarithmic differentiation, okay? So if we use, so by logarithmic differentiation, okay? By logarithmic differentiation, what I'm going to do is multiply both sides of these by ln. So ln of y equals the ln of x minus 2 quantity squared over the square root of x squared plus 1. Okay. And then the reason I'm doing this is because we know that on this side here, ln of a quotient or any division is really implies subtraction. So this can be simplified. Simplify this. So now we have ln of y is equal to ln of x minus 2 squared minus, because division, ln of the square root of x squared plus 1. Okay? If we further simplify this without taking the derivatives, because we know all of these derivatives, this is the same as ln of y equals to ln of x minus 2, okay, squared minus ln of x squared plus 1 to the 1/2 power. Okay? So all we did here was rewrite. Now we know we're going to rewrite again because in logarithm, all of the exponent becomes a product. So we have ln of y is equal to 2 ln of x minus 2 minus 1/2 ln of x squared plus 1. And now we take the derivative of each one of these. And remember the derivative of ln of u, right? Ln of u is u prime over u, okay? So you may want to recall, okay? So if we recall that d dx of some function ln of u is equal to 1 over u du dx, which is really u prime over u, okay? So if we apply that here, we have something totally different now, okay? So ln of y, here is my u, this becomes y prime over y is equal to 2. Here is my, this is, let me highlight, this is my u, this is my u, and this is my u here. So u prime here would be the 2, okay? When you take the derivative of x minus 2, you get 1 over x minus 2, okay? Minus, keep the 1/2, and then the derivative of this x squared plus 1, the derivative of x squared plus 1 is 2x plus 0 over x squared plus 1. So these here, these, what is my u? This is my u, this is my u, and this is my u, okay? And the derivative of y with respect to x is just y prime. So if we simplify, we have y prime over y is equal to 2 over x minus 2 minus 1 times 2x is 2x over 2 times x squared plus 1. Okay. If we find a common denominator, we can combine into one fraction. So y prime over y is equal to, the common denominator is x minus 2, okay? This here is the same as 2x squared plus 2 if you want, okay? So times 2x squared, 2x squared plus 2, So if we use algebra to simplify this, this becomes 2 times 2x squared plus 2 minus 2x times x minus 2. Y prime over y is equal to 4x squared plus 4 minus 2x squared minus 4x. And we don't multiply out the bottom. If you want to multiply it out, you could multiply it out. I will leave it the way it is. So we have y prime over y is equal to, gather like terms. We have like terms, okay? So this becomes 2x squared minus 4x plus 4 over x minus 2, 2x squared plus 2. Now notice I could, if I want, I could factor out a 2 from the top. So this becomes 2 times x squared minus 2x plus 2. And the bottom I can also factor out a 2, right? We have a GCF of 2. So this becomes 2 times x minus 2 times x squared plus 1. And then this 2 can cancel with that 2. So we have y prime over y is equal to x squared minus 2x plus 2 divided by x minus 2 times x squared plus 1. So finally, we can see that y prime is equal to y, taking the y to the other side, times all of this, x squared minus 2x plus 2 over x minus 2 times x squared plus 1. So it doesn't look as nice as what you may want it to look, but it's still the derivative. Now, keep in mind that you were given y from before, okay? So you know what the value of y is. Y is the function up here, okay? So this here is your function y. So we can plug in what the value of y is. So finally, final answer is y prime is equal to y, which was the value of y, is x minus 2 quantity squared over the square root of x squared plus 1. And then I'll multiply that by x squared minus 2x plus 2 divided by x minus 2 times x squared plus 1. And I'm sure if you want to simplify this even more, you can. We can make it written into one fraction. Okay? We can write this as one fraction. So, but I will take this as an answer, or you can simplify more. So this, I'm going to repeat that this is just, I choose to use logarithm here to help. Like I said, you could have used the quotient, right? You have two options. Use the quotient rule, okay? So I would strongly advise that you try using the quotient rule and see if you get the same answer for this particular problem, okay? I hope this helps with implicit derivatives, okay? And we'll try some assignment problems.